Okay, let's start. Welcome everyone for the afternoon of this fourth day of the JuliaEO workshop. We'll now have a talk by Mr. Simon Lupemba entitled of the Dirt Observation Processing Chain. And Simon, the newest addition to the Scatterometry team at EUMETSAT, contributes to the operational observation of ocean winds needed for global weather forecasts. His daily work involves using Julia to monitor and maintain processing software for the ASCAT instruments aboard the METOP satellites. Additionally, he contributes to developing software tools for the upcoming SCA instrument on the METOP second-generation satellites. Simon holds an MSc in Earth and Space Physics and Engineering from the Technical University of Denmark. His interest in Julia began during his studies in 2019. After a 2-year period of working with C on medium-sized public IT projects in Denmark, Simon eagerly embraced the chance to return to scientific computing with Julia upon joining EUMETSAT. Simon is excited about the potential to use Julia to improve the processing chain of Earth observation and wants to play a part in the realization of this potential. Thank you.
Thank you for the really nice introduction. So, I don't think that's much more to introduce. I think I'll just start the talk. To the title I added scatterometry as an example, and that's because I work with the scatterometry instrument, and that's kind of my speciality. So the talk is going to focus on that as an example, but some of the things I present also applies to the other instrument and data sources. So first up, here's a short agenda, and I'm going to start with a quick introduction to EUMETSAT. I think that gives a better context for the presentation. Then I'm going to go through the EO, our processing chain. So it's like the data come from the satellite and what happens before you actually download it from some data hub and use it. And then I will talk a bit about how we use Julia in my team and at EUMETSAT. And lastly, I will present my personal view on Julia for EO processing. And I say that is my personal view because I don't think EUMETSAT have any official view or thing. So, I mean, it's not the whole organization. And the conference is called JuliaEO, so I thought it was also good to have like something really focused on the Earth observations part. So first introduction. EUMETSAT is an intergovernmental organization with 30 member states, mainly located in Europe. It's not the same as ESA or EU, but there's a large overlap in a lot of the member states. So therefore, we also have a large amount of collaboration. But we have our own set of member states that we serve. Our primary objective is to establish, maintain, and exploit European systems of meteorological satellites. So that's meteorological satellites for weather. And then we have the further objective that is to contribute to the operational monitoring of the climate and the detection of global climate change. What this kind of means for us in practice is that we focus on meteorological satellites and long operating programs to ensure that we have stable data for the weather models and the forecast, but we do not create weather forecasters at EUMETSAT. This also means that a lot of our satellites rely on like well-tested and well-proven measurement concepts and technologies, because we're not so much a developing agency trying to make the next cutting-edge instrument. We need to have something well-proven that can work for a long time. And also a difference that's worth to noticing about these two is when we do weather data, like data for weather forecast, it is extremely important for us that we deliver it fast to the meteorological organization and to ECMWF, the European Center for Medium Range Weather Forecast. So speed is really a essence there. Whereas if we talk about the climate, it's okay that the data is old, but for the climate perspective, we also are committed to when we improve the processing software, then once a while we do a reprocessing campaign where we also reprocess and improve some of the historical data, or I mean just data that's too old to be used for weather forecast. Yeah. Here's an overview of some of the European satellites ESA developed, but we have this, all the orange there, which are the meteorological satellites, which are operated by EUMETSAT, and then in the middle we have the Copernicus satellites, which is funded by the European Union, and some of them are also operated by EUMETSAT, and we maintain some of the processing for them and the ground segments. But yeah, as the slide says, ESA is involved in the development of the satellites to start with. Yeah. I just wanted to show this slide to show like some of the time frames we work with. So I'm going to talk about an instrument on the MEDOP satellites, where we have A, B, and C, and that's been up. Like the first one, the MEDOP A, I think it started operations in, it was launched in 2006, and it has been decommissioned now, but we still have MEDOP B and C that are providing data. And then I'm also involved in the preparation for the next generation, so that is the MEDOP second generation, which we will launch in the coming years. And that's, as you can see from this slide, it's planned to operate into 2045. So we're planning this program for 20 years. So we're really trying to work with some long programs and long time scales. Yeah. So that's enough about EUMETSAT. Then let's dive into the instrument I work with. This is a rendering of the ASCAT instrument on the MEDOP satellite, and maybe I just jump to the next because I think that's more fun. This is the new one, the SCAR instrument on the second generation. First of all, they look alike. So it's because they use the same measurement principle. The new instrument is just better and have a bit more capabilities, or like have more capabilities in area. But the principle is kind of the same. It has these 3 arms that extend out from the satellite, and each arm have 2 radar antennas. So the panel you can see on each side is actually an antenna for the radar, scatterometer radar. So in total we have 6 radars, and as you can see there with the people at scale, this is not a nano satellite. I mean, we're talking a big instrument that is launched. Yeah. I'm just going to show this for the measurement principle quite quickly. So why do we have these 6 antennas, you might ask? And that's because we want 3 of them to point to the left side of the satellite and the 3 others to point to the right side of the satellite. So when the satellites orbit the Earth, it tracks out 2 swaths, one on the right side and one on the left side. And in each swath, we image each pixel by the 3 different radars. So we got 3 observations, which will become important later. Yeah, and I mean, the measurement principle is a little bit the same as the SAR satellite with less processing, but as you can see, this is geared differently, and it's also because not only do we want the 3 observation, we also want a really huge swath, because for weather it's important to cover the entire Earth. And it's important to do it regularly in time. So I mean, we don't have a good spatial resolution, but the temporal resolution is quite high. Yeah, so that's why it's designed like this. And I think we had some presentations earlier where you talked about Sentinel-1 and Sentinel-2 images, where you often have the thing of not having any images over the oceans. This is not like that. We try to image everything. Yeah. Oh yeah. In the next, to understand the processing chain, it's okay to like know a little bit about the normal terms used for the different processing levels. So this is like these. Processing levels are normally used by NASA, ESA, and EUMETSAT, and more. I didn't go into depth if anyone else were also using them. But what we normally have is that we start with level 0 from the satellite, which is just these raw observations. So it's actually the things analog to digital converter kind of measures in the instrument on the satellite, which is we then get down. And then we have the level 1B where we transform it to, we geolocate it, position it on the globe, like where's the measurements actually from, and we also do radiometrically calibrated backscatter. Yeah, I didn't write backscatter there. Radiometrically and geometrically calibrated geolocated data. And it's because, I mean, some of these things, these things is not only applies to the ASCAT, but also other instruments have this. So you start with the raw data, and then you do some calibration and corrections and geolocate, and then you have the level 1B. And then normally when you get to level 2, it's because you start to derive geophysical properties, to know more. How does that look? I made a small picture here, a small diagram. I think it's quite easy to understand, but we get the data down from the satellite using a ground station. It's fed into a level 1 processor, which take the level 1 data together with some auxiliary files, spit out level 1 files, and these are then disseminated, sent out in real time to meteorological services and super users that want them real time, and then they're also placed on the data store in the archive, so we save them. And then we also take it to a level 2 processor, which then process the data to level 2 products, and then we send it out. I'm actually mainly involved, and my team is with maintaining and updating the level 1 processor. So I mean, I know a bit about the rest, but that's really where I know the most. Yeah. Okay. So enough abstract concepts and slides like this. Let's try to look at a more concrete example from the ASCAT instrument. So here I've taken some level 0 data, and it's really the instrument data. So for this instrument, it comes in data records, which is you get like one data record from one antenna, and then you get one from the next antenna, one for the next antenna, then one for the next antenna. In our case, it contains the antenna ID, and we also have the echo and then some noise measurement and some internal temperature measurements. And all of this is in unsigned integers of some sort, which corresponds to what the instrument actually measures. I like the analog to digital converter and the onboard processing. The only like dimension we have, or like thing we have, is we have timings from the onboard clock. So internal timing. So that is what we later use to geolocate the observation and find out where it is on the Earth. But at this point, we actually only have the time of the measurement. And then, I just put some data rates. So right now for ASCAT, we have some onboard averaging, so it's not so high. And that's simply to save on the data rate, because downlink is both storage on the satellite and downlink is like a constraint. But on SCAR, the new generation, we luckily don't have any onboard averaging, so there we will get one data record down for each pulse the radar sends, and that will allow us to do more complex analysis and maybe even derive some new products. So I really look forward to get my hands on that real data once it's launched. And maybe now. I could have said it earlier, but now just going to talk a little bit about like what this big instrument is actually used for. So I mean, we send each radar antenna are used to send out a pulse, and that hits a surface, the surface of the Earth. And if the surface is flat, plane, then it's the echo is reflected away, like the signal is reflected away. But if there's roughness or anything else, part of the signal is reflected back to the satellite, and that is what we measure with the echo. And as you can see, if you go, I mean, it's a good day to understand that high winds causes waves and roughness on the ocean. So the whole principle about this, at least for the wind retrieval over the ocean, is that the stronger the winds, the more backscatter and the higher the echo is. Yeah. So level 1 processing. So what do we actually do to go from this level 0 to the level 1 data? We have the processor and we have the level 0 files, and they are, of course, really important for the processing. Those are the ones that change all the time. But to locate to map these unsigned integers to actually backscatter values, or like what comes back, and to apply some corrections, we need to know a lot of information about the instrument. And that we have in some auxiliary files, which is also fed in. And that is where we have the characterizations of our antenna and our gain patterns. And we also have like some of the physical things, like which way does the antenna point relative to the satellite, and things like that in the auxiliary files. And then we also get the orbit state from the satellite. So which orbit is it in? And we also propagate that orbit state to find out where is the satellite at the different timings that we measured our instrument. And these timings are then used to geolocate the data and find out at this, like when this measurement was taken, the satellite was at this position, and the instrument was pointing in this direction. So therefore the observation must correspond to this place on Earth. So that's kind of the process of geolocating it. This also means that, I mean, of course you don't see that in higher level products, but normally when you have something like this that is a polar orbiting satellite, or in general you have Earth observations, a lot of the observations actually have slightly different timestamps if you go into details, because it's often like one observation are taken one by one, or there's a scanning instrument on the geostationary satellite scanning the Earth to make an image. I mean, for a lot of use cases, it's nice to just have one timestamp for the entire file, but it's just sometimes good to know in reality that the time changes throughout the files, and also that once we do this mapping from time to geolocation on Earth, it doesn't end up on a regular grid to start with. Regular grids in Earth observations, that's something you get to by resampling the data. I don't think it's native to any instrument. Yeah, okay. And then I have an example. This is, I'm just going to show some full resolution data using Markey and Taylor because it's good packages. And so here I just plotted the backscatter in decibel over an area. It's like a 3-minute slice, and this is from one of the antennas, what you see. And what you see is that you have the coast, which is a bit brighter, the land, and then you have the ocean, and you have different structures on the ocean depending on the wind speeds. And if we go out a bit, then I also did like this, made a little slider, so we can see that the different antennas, if you take the same stream in the slice, the different antenna covers different parts of the globe. Yeah, so like this is some 3-minute slices from one side of the satellite, and then we have the same 3-minute slices from the other side of the satellite. Here. Yeah. So this is an example of a level 1B data where we have converted it to backscatter values. So this is in decibel. And also have geolocated it because otherwise I couldn't plot it on a map. Yeah. So let's go. Oh yeah, and I have another. So one thing we do, we have several level 1B products for ASCAT. And one of them is reduced resolution. And here we have, the first was the full resolution. This is a reduced resolution. But here we have resampled the observations from each swath to overlap. So we have 3 values, 3 backscatter values for each point on each in each swath. And there we have like the backscatter for the forebeam. It's the antenna beam that points slightly forward on one side, and the mid beam directly to the side, and the after beam. And I also just scaled that from in some dB and plotted that as an image to show here how that looks. But I mean, it's not easy to see what's going on based on the colors. And the thing is, if you rotate the satellite, the colors change. I mean, these colors depend on the direction of the satellite relative to the things you're imaging on the Earth. So this plot is just for to show that things are working and like how to visualize the data. But in practice, a plot like this is not so useful for anything else than debugging if something is going on with the processor. So I mean, I could use it sometimes. Yeah. Okay. So this is the level 1. How do we go to the level 2? So like one of our level 2 products, and it's mostly like, it's important for the weather models is wind and wind directions over the ocean. And actually this is not done so much directly by us as it's done by the KNMI, which is the Dutch Meteorological Service. So we have a collaboration, and it's like that with many of EUMETSAT's higher level product that we collaborate with different institutes in member states that does some of the higher level processing or maintain some of the software to do this. So this I'm going to talk about is some models from KNMI. We have a model that relates the wind speed. We have a model that relates the wind speed and relative wind direction, and that's the wind direction relative to the antenna, and then the incidence angle to which backscatter we expect. So for a given incidence angle it's determined by like how far out in the SWOT you are, and then the relative wind direction and the wind speed. And I also have some plots to show that. So if you take all, so if you take that model I showed there and you fix the incidence angle, and then you take it for a configuration of our satellite, and then you run through different wind speed and wind directions, then it outputs like a surface like this we're shown here, which we sometimes call the wind cone. And you can see the axis is what backscatter did we expect to measure in the after beam, the mid beam, and the fore beam. So we have our three different antenna beams. We take the observations there and map them to an axis. The red dot shown here is an actual observation from the instrument. So that's actually one of the observation points from the reduced resolution product. So I just plotted it there to show that it's kind of lies on the surface. And here I made some sliders to show that the blue dot just matches the sliders here. So you can see as the wind direction change, what we would expect to observe. Oh, that's not the wind direction. As the wind direction changes, what we would expect to observe with the radar, with the instrument changes. It kind of rotates around this cone, what we would expect to see. And as we change the wind speeds, then it moves like up and down, because high wind speeds we expect like a lot of backscatter from all beams. Low wind speed we expect low backscatter for all beams. So finding the actual wind speed and wind direction can be seen a little bit like having some sort of software that moves these sliders around until the model matches the observation. So for example, in this case, it might be that we say that we expect the wind speed to be around 16 meters per second, and the direction is probably around 60 degrees relative to the mid-beam. And there's a surface inside a surface here. So it's kind of twofold. I think I have like a slice of it here, which make fitting things a bit harder. Slow here. But like this is just a slice of the cone, so it there's some ambiguities for some special directions and things like that, but it is also not supposed to be too easy. So this is done. I wrote OSISAF here, which is the Ocean Sea Ice Satellite Application Facility. It's done by KNMI via them, but it's done by EUMETSAT partners. And they to make level 2, they estimate wind speed and direction based on the level 1 backscatter. This product for wind speed and wind direction is only done over the oceans. They also have some algorithm to kind of correct for ambiguities. In the product, they also include some quality flags and some distance to the model function to kind of show like how good the fit is. And I have an example here let me see. I think this example is one that matches the data I showed before. So the 3-minute slice where we have some wind speed around, and maybe I can show like here. So we have the wind fields here, and the red ones are flagged. We automatically have a flag for everything close to land that it might be affected. So I mean, and we also use a flag for really low and really high wind speed. So just because it's flagged, it can still be useful. But I don't want to spend too much on this because just before the presentation, I got the latest product over their source. So this is from, this was taken between 9:30 and 11 today over the island. And as you can see, we have really strong winds. I mean, I don't have any scale for the winds here, but it's quite an intense wind field. It's even, I think even some of the values in the wind field that are not near islands are just flagged just for being strong, because it's also hard for the model to fit the really strong winds. Which, I mean, this is for ASCAT. In the new instrument SCAR, which is being launched, we will be able to better resolve the high winds. So I mean, we have really good coverage here. Maybe I skip this demo because of the time, so I also have some time to answer questions. But of course, we don't throw all the information away over land. We have some soil moisture product based on our data. I actually just show quickly. Yeah, so we have some soil moisture data because you can also see soil moisture using ASCAT. And what we see down here is probably a desert. So we don't throw the data over land away. We also use that. So fast. Next. Yeah, so beyond level 2, I'm not an expert, but apparently we also have a level 3 product, which is the Global Sea Ice Edge. And here it's not just based on ASCAT data, it's also based on microwave radiometers. So what is done in this product is that they aggregate all the data over the polar regions for an entire day, both the ASCAT, the scatterometry data, and the microwave radiometer data. And then based on the whole combination of this data, they estimate the sea ice extent as a daily product. And with not too much confidence, I think this is like a good example of like a higher level product that, first of all, you start to diverge from the. You don't just use one sensor anymore. You use multiple sensors. It's not really in the grid that follows the satellite anymore, but you have like average over a period of time to make sure you have a region data field, and then you also you use information from multiple instruments, even on different satellites. Yeah, how we use Julia on my team. Julia is a niche at EUMETSAT. There's not so many that's using it. I know my team is using it. I mean, I'm using it a lot, and 2 of my colleagues are using it a lot. Some others of my colleagues are using it a bit. And then there's another team with another instrument, the infrared team, that is also using Julia. But I mean, compared to how many we are at EUMETSAT, there's a lot of people who don't know what it is, if I say it. Have no idea. Yeah. Then what I'm using it for is like, we use it for visualizing the data, monitoring of the science data, seeing everything is all right, tools for calibration, regression testing. I have some tools to compare some data, prototyping, and then lastly, Julia is not used in the operational processing chain. So it's not there yet where the manage like the people where people feel comfortable enough to actually use it in the operational processing chains. It's for some of these also really important items for making a mission work, but like I mean most of these things are not time critical in the same way. Yeah, and then my personal view on Julia for Earth observations, and I mean I must say it's my personal view because as I said before, most people at EUMETSAT doesn't know about Julia, so they probably don't have a view on it. I see there's a lot of opportunities because what we need is high performance scientific computing, and that's what Julia is made of. The composability could improve like that we do more reuse. I would also like that we had more open source, like that we publish some of the things, not only the tools for the users, but also some of the processing we actually do. The flexible data types is really good, and I mean it's powerful that Julia is so flexible because sometimes we have weird things like a complex number, which is I think we have a complex number which is 24 bits in total. So that's 12 bits for the real part and 12 bits for the imaginary part. Which is, I mean, it's quite nice to have a language where it's not so hard to work with this. And then we have some challenges, clear challenges. First of all, EUMETSAT is not a general first mover. We have long operational programs. We need long stabilities. The operational chain really relies on well-tested, well-proven technologies. Everything that is called breaking changes is everyone gets scared. Awareness, people at EUMETSAT simply don't know about the language. I mean, some does, but like there's also a lot that doesn't. We also have the industry uptake as a challenge because a lot of these processing software that we're using operationally, we put out tenders for companies to bid on, and then the company delivers the software for us that we use. So we do the specification and sometimes also some prototyping. But in that scenario, it means that both the companies that are actually building some of these components and EUMETSAT should both be comfortable with the idea of using Julia in operations for this to be a success. Yeah, maturity, again, like everything called breaking changes scares people at EUMETSAT. So and also like the tooling for doing it, it's okay that the language is flexible and there's the potential to build tooling, but of course there's like a tendency to stick with the languages where the tooling is already there. And I mean, especially if the tooling is already in-house and the expertise are already in-house, that, I mean, you can do it because you have done it before. That's sometimes easy to fall back to. And I mean, also just when you run an operational program for 20 years, you don't want to risk of jumping on a trend that just disappear, and then suddenly you cannot recruit developers or anyone that want to work with it. So there's a bit of comfort in being a part of what the larger community does. Yeah, and last thing, I also have open source versus proprietary information. It's not always the view that at open sourcing things are good things, because sometimes we also, I mean, a lot of time we also have contracts with companies where they get to keep part of the intellectual rights when they develop software for us, and that's supposed to like help the European industry grow. But I mean, it also kind of conflicts a little bit with the whole open source idea. Yeah. the road forward. So what I hope to do, and I hope where we can go. So I hope to publish a package I made. I think it's for reading and handling the ASCAT data, because I think it's important with like an open source community like Julia. When you're part of a big organization, also to engage with it and give back, not only take. I hope to contribute to open source packages relevant for EUMETSAT. Then I hope that we're able to prove the value of Julia through non-operational tools in the organization. So we're not going straight from the operational tools, but for the prototyping and the calibration. Then keep an eye out for first movers. I'm really hoping that other organizations, our partner organizations like ECMWF or ESA, or some of them also picks up Julia, so there can be a bit of synergy. And then, I would try to just advocate for Julia inside EUMETSAT. And the last slide I have is how can you help me transform EUMETSAT to use more Julia? So first of it could be nice if engage. So we have like a lot of data up on a data platform. I mean, most of our data is freely available, so you can go there, make cool stuff with Julia and the data, and then maybe be a bit vocal about you use Julia. Because I mean, right now I think the general view is that we have a large Python user base. So once we develop user-centric tools, it's for Python because that's what the majority of our users use. And then we have a meteorological satellite conference in Germany here in the summer. And I would love to see some Julia users there, or like some Julia relevant presentations. And there's a special early career scientist initiative if you are under 32 and have under 2 years of work experience. So that also includes if you're a PhD student and something like that. And so maybe check out the data, check out the conference, and then I hope to see more Julia users in this space. I just show quickly the data store. So here we have an example. You go to the data store, you choose ASCAT coastal winds, and then you can access the data. But you can access the data and download like a whole orbit of wind estimates and wind direction. So like just some side notes to this. Right now, this visualization of the footprint for the level 2 data, that's a bug. And I have reported it, and I think they're working on it. So if you choose an area and like download the data and it doesn't fit completely, I mean, they're working on that bug. But I mean, for the level 1 data, it fits. And also, I mean, it's only the level 2 data, which is in a nice netcdf format. When you go to the level 1, we have our own binary format. That is the thing I hope to solve with the ASCAT data package. And lastly, we also have a user portal. And I mean, I don't know a lot about the user portal. You can Google it, but it got launched 2 days ago. So it's completely new. But like they're doing more to make the data more easily accessible. I think I use my time now.
You? Claro? No.
I know you said it earlier that this has nothing to do with you, but do you know how to become a super user?
Like super user?
Yeah.
Of what?
Of the data. You said that super users can acquire the data earlier.
Yeah, okay. So that's sometimes. So I went over it briefly in the start, but we have two different ways of accessing the data. We have the data portal, which is the easier one, I would say, and it's just made to like get some data on demand. But then we have like a lot of infrastructure to streaming out the products in near real time as soon as we process them. So they're put out, and that's called Humidcast and maybe Humidcast terrestrial. So like the Humidcast, you actually need to have like a small parable, like a small antenna, kind of like Starlink, and then you can like get it really fast. And for the terrestrial, you just use the internet. But there is, I mean, a lot of our focus is on the meteorological services, and they need to just get the data out as soon as we've processed it. And I don't know if like what it requires for private persons to sign up, but I mean, I think you can do it through a university also. Yeah.
It's a very interesting product, and what you do for modeling would be very, very interesting. And I was also thinking on how good it represents coastal winds. Is there some kind of limitation? Have you, I mean, you or other people have done comparison with buoys that has meteorological instrumentation? So,
with the wind buoys, one of the most obvious thing is our spatial resolution. So we have, like, I mean, I think the data I showed was on a 12 by 12 kilometer grid, and when you average like the wind speeds over such a large area, you get like a significant like you get a different distribution compared to like point measurements for wind buoys. Yeah, so that's like one thing. If you like try to compare them one to one, you should like account for the resolution. The same if you compare it with anything else. Yeah, and then on the second, like if we have any known biases, and there is one known bias, and that is this is equivalent wind stress. So this is the wind, the wind movement relative to the ocean. So all ocean currents, like stable ocean currents, are going to be an error in our wind estimates. So that's one of the things. We are like actually hoping really much with the SCA instrument and with the not having the onboard processing that will be able to better correct for the ocean currents. So ocean currents is definitely one thing. And yeah, I think that's it. And of course, I mean, there's also, I think there have also been tests of like using information about significant wave height in general, like if you have larger waves to correct that are not caused by the wind. But I don't think that's a big thing. I mean, it is possible, but I mean, the bias they talk most about is the ocean currents.
Thank you very much.
Yeah.
Yeah, I found it very interesting that you mentioned this challenge for an organization like EUMETSAT that whatever software is developed there, even though we would like to have it open source, right? I mean, the idea of Julia obviously is also doing open source things, although it's on an MIT license, so you can also do a lot of other things with it. But still, I find like for a lot of these big organizations that are, I mean, EUMETSAT is like funded through some member states. So I think the organization is very similar to, for example, ECMWF. And I do understand that obviously there's a lot of money put into something that they don't necessarily want to put it right out as like MIT license, and some kind of company could run away with it and just make a bunch of money with it. But I still don't understand why these companies are so resistant to putting it under any other open source license where they can basically dictate their own terms of like, hey, you can use it if you're like an individual, but for example, it's a non-commercial license, so you can't make money with it, right? And I feel like there's really that, I think we as a community, as open source community, you really have to push for these, like this whole gray zone in between, let's say, super permissive MIT license and having everything closed source, because otherwise I feel like we always reinvent the wheel. We always do like, oh no, they have already done this, but they're not allowed to share this. And I feel these institutions are always lagging behind, and it's like, it's really frustrating.
But I couldn't agree more. But I mean, I think my view is a bit biased in that sense, because I like Julia and I like the open source. I think the big idea is at least that once the European companies develop something for EUMETSAT, then they get to keep the license and keep it so they can resell the software or like use it in some other commercial products, and thereby stimulating the European economy and the economy of the member states. And the fear is that if it's just put out, then they won't have this opportunity, and you won't get the industrial stimulation of the programs that is also part of it. So yeah, I think that's one. But I would say, like at EUMETSAT, we're controlled by the member states, and the member states have delegates in the member countries. And if a lot of the delegates at some point would say, we think you should open source more, then EUMETSAT would do it. So it's also like that. It's also, I mean, we're really I mean, we're advising the delegate, but like we're doing what the council tell us to do. So a larger change in an organization like EUMETSAT could also partly and something come from the council. So find your local delegate.
Thanks for this great talk. So, in the plot that you showed, you maxed actually quite a lot of data near the coast, and it didn't obviously look wrong, the wind arrows that you showed in red. So, I'm wondering if there's some data that can actually be recovered, so that even if... So, are you sure that they are bad, or are you just prudent to not to show them?
Yeah, okay. So what I showed here, it's like I mean, I know I colored it red, so it looked bad, but I just showed any flag as red. I mean, the flags, there are individual flags, some for quality, some just for being close at land, some for being there. So I mean, I think if you look into the actual flags, you would find that some of the ones near the coast are flagged as being of good quality, like still seems to be of good quality, don't have the poor quality flag. I just, to make a fast visualization, I put all the flags together and like colored it. But I mean, if you look at the individual flags, and I mean, there's also one thing they really use is also the distance from the cone, wind cone I shown. So like if you have some contribution for the land or something in one of the beams, what you would often expect is that you get a point that does not lie on the surface of the model, and therefore that's like actually one of the main tools to really discard data.
I have another quick question, if I may. So, what does the process look like to choose a language at EUMETSAT? Can somebody use just by themselves to choose Julia or another language, or is this more group-wise or institutional-wide decision what to choose?
So it's actually like at least in my department. I mean, there's there's an advice to like kind of align with the team, and I think that's also the general approach. But there's also some freedom for the individual teams to choose their day-to-day language and what they do. There's quite a lot of I would say expert freedom for the experts to choose themselves. But as soon as it goes for the operational tools and we go for tenders, then I think, or like when it comes to deploying things in the operational pipeline, I don't know the process, but there's like a lot of checks and a lot of people who have to agree. And I think for the last tenders, for like some of the processing for the SCAR satellite, which we have now, I think the company could choose, like the company that delivers for us. I mean, I think of course it had to be approved, like what they bid in with, but I think they could choose the language when they made the bid.
Thank you very much again.